let's take a look at a Bayesian approach to naive Bayes classification. So it's a Bayesian naive Bayes. Naive Bayes, we looked at a couple methods for estimating the parameters of a naive Bayes model using maximum likelihood estimation and maximum a posteriori estimates. But in this, so here we're going to think about how to take a fully Bayesian approach, as they say, and actually compute the posterior predictive distribution of a class given, for a given x and given some data. So this is nice because in a certain special case, we will be able to compute this exactly, and it's a pretty simple, nice example of a fully Bayesian approach. So we're going to consider the special case when all the features are categorical, so they all just take finitely many values. All right, so in any classification algorithm, we are given some data. So we have our x's and our y's. It's a supervised setup. And so let me change this to superscripts here, since I want to make sure to keep a clear distinction between the different points and their features. So I'll use superscript for the whole vector, and so x superscript I, that was a mess, is this vector of values x superscript I subscript 1 up to n. And each of these will be, so we're going to take these to be categorical. So each of these guys, x, I, j, is in some finite set. Maybe I'll say like a, j for the set for the jth feature, the jth coordinate. And y, as usual, the y's are just in some finite set. I'll use capital script y, and let's just label them the classes 1 to n. Okay, so this is what we're given, and in a naive Bayes classification model, before we get to the naive Bayes assumption, in general, we're always going to take some sequence of random variables to model our data. So we'll have x1, y1 up to xn, yn. That's the different points. And these will be all distributed according to some joint distribution on x and y given a parameter theta. So we're going to parameterize these joint distributions by theta. Oh, and these are independent given theta, because I emphasize given theta since we're going to put a distribution on theta. I sort of suggested that already since I was conditioning on it. Okay, and now we get to the naive Bayes assumption, which is this joint distribution. Well, we can always factor it as the probability of x given y and theta times the probability of y given theta. But the naive Bayes assumption, let's move this over to the left, so that just stays the same. And the naive Bayes assumption is that the product, let's say as j, we'll use j for the feature index. Product as j goes from 1 to d. Did I say d? Oh, that should be d. Sorry. There's d features, not n. D. Whoops, what happened? It's a d-dimensional vector. So the product as j goes from 1 to d of the probability that the ith coordinate is little x j given y and theta. So we're we're just factoring this. This is the assumption, the naive Bayes assumption, that the features are conditionally independent given the class. And here it's also given this parameters. Okay, and now we need to define our model. We need to say what these distributions are. So we need to define these distributions. So we need to define, let's maybe use a different color, probability of y given theta. And this is just going to be some categorical distribution, because y just takes finitely many values here, 1 to m, and it's parameterized by theta. Let's call it, I don't want to call it theta because we're going to have more parameters, so let's call it pi. Pi is often used for, so it'll be pi, I'll say pi of y. Pi is going to not be the number pi, but it's just a vector of numbers here. So pi is going to be just the vector of numbers pi 1 up to pi m, since there's m of these. Okay, so pi is the distribution on the y's, and we'll say for this xj given y and theta, let's call that our what do we need here? So it's for on the jth coordinate. So for each of these j coordinates, we need to have a different distribution. Remember, maybe I'll write out here what this is. This is the probability that xj, the jth coordinate of a generic point. We're considering sort of a generic point x and y that are distributed according to this thing here. And this is the probability for this generic x. This is a d-dimensional vector, just like this. The probability that equals the value little xj, given that y equals y, this y here, and given our parameter theta. And this, let's call our, okay, so we need a different one for each coordinate, each different j, each different feature, and also it depends on y. So for each different value of little y, we're going to need a different distribution. Well, it is a different distribution. So we need a different distribution for each j and y. So let's subscript this r by j and y to denote that it's the distribution on the jth coordinate given little y. And it also depends on the value xj. So this is the distribution, and this is the xjth value of that distribution. So it's just a finite vector like this. And the number of components in the vector coordinates is the number of values in this set aj. Right. Okay, so those are this is the categorical assumption that we're making here. This is a special type of naive Bayes model. All right. So maybe just to be perfectly clear here, this pi, maybe I'll write, sort of want to leave some space over there. So the sum of the pi's is sum of the pi's over y is 1. This is a distribution, and the sum of, as let's say k for this little xj, ranges over aj, that set, then rj of y of k, r sub jy of k is 1. And these are all non-negative numbers. And this is true for all j and y. This is for all j and y. Just to be perfectly explicit here. All right, so this is okay, so we haven't really done a whole lot new here. So where's the Bayesian part? Well, we need to put a prior on theta. Oh, so I should say what theta is here first. Let's see. So I sort of wrote theta as a generic parameter, and then I put theta here and then pi over here, and I put theta here and this r. Where's theta and where's pi? So let's just define theta to be the pair. Where do I want to put this? I'm trying to save. I'm saving space over here because I want to draw a picture. But so let's just write it here. Theta. I'll put it up here. Theta is going to be the pair pi and all the different r, j, y's. Each of these, for each j and y, this is a distribution. So this is the set of all those distributions. So theta is all of these different vectors, which each of them defines a little probability, a little categorical distribution. All right. So that's the basic setup, and now we need to put some priors. All right, so we're starting to get a lot of stuff here, and I want to draw the picture that I've been alluding to keep everything straight. But there's a simpler way to describe this, but I want to just go through all the details so it's all very clear. All right, so here's the picture. So we've got y. I'm thinking about our generic x and y here. So y, I'm just going to draw this little picture to keep track of stuff. We've got our y, and x. That x is just a vector of these different coordinates. So x1, maybe there's just 3 of them, just to keep things simple. x2 and x3. And these depend on y. So I'm drawing a graphical model if you know what graphical models are. And then x1 also depends on this r1. It's 1 for the first coordinate. So j is 1. This is j here. J is 1. And y, little y, and let's say, so y goes from 1 to m. So we'll just put all those together. Which one it uses is going to depend on what y is. And here we have r2,1 to r2m. Each of these is a different distribution, and r3,1 to r3m. So the process by which this data is drawn is that we choose a y, and then we choose an x according to, let me put one more piece here. We choose y according to this distribution pi. So we choose y according to the distribution pi, and then we choose x1 according, so if y is say 2 or something, then we would choose x1 according to the distribution r subscript 1, 2. And if y was 2, we would choose x2 according to the distribution r subscript 2, 2. And we would choose x3 according to r subscript 3, 2. Okay. And should we go on to that, or maybe come back? Let me stop there in this video, and we'll come back and we'll talk about putting some priors on these pi's and r's, and then we'll be in Bayes land, and we'll be doing Bayesian inference. All right, see you soon.